In this video, I introduce semi-supervised learning through entropy minimization. Semi-supervised learning learns a decision rule from labeled and unlabeled data, namely learning the high-level structure of unlabeled data and only relying on labeled data to learn the fine-grained details. Given a training dataset L n with L labeled data and the U unlabeled data, if a random variable h is used to encode missingness, h is equal to 1 for a hidden y, and h is equal to 0 for observed y. The missing probability at random assumption is expressed as here, which means the probability of a data point having a missing label depends on the known features of the data itself, not on the actual unobserved label. Assuming independent samples, the conditional log likelihood is computed by using this formulation. Without assumption on px, maximizing L with respect to theta is not related to the second term as shown here. Namely, unlabeled data has no contribution to the maximum likelihood. Using unlabeled data requires assumption relationship between x and y. For example, in the MAP framework, contribution of the unlabeled data is encoded in prior, as shown here. This Bayesian theorem, this posterior, this likelihood, this prior, and this margin. Conditional entropy is related to the usefulness entropy of unlabeled data, where labeling indeed ambiguous. Hence, the measure of class overlap is a condition on missingness, as shown here. Using integral to replace expectation, we have this formulation. This P is a density function. In the MP framework, assumptions are encoded by means of a prior on the model parameters, as shown here, where lambda is positive Lagrange multiplier. H is approximated by the empirical distribution, as shown here. Using the random assumption here, HEMP is rewritten as this formulation, which applied to compute the empirical prior p theta on parameters theta. The MP estimate is defined as a maximizer of posterior distribution, as shown here. And this is the likelihood term, and this is the entropy regularization term, where lambda is used to weigh distribution from the unlabeled data. While L is only sensitive to labeled data, HEMP is only affected by the value of P on the unlabeled data. The goal of semi-supervised learning is to maximize the criterion C with a term of entropy regularization. That is to improve the prior distribution. In other words, improve the model confidence by minimizing entropy regularization term as shown here. Deterministic annealing expectation maximization algorithm is applied to maximize the criterion C, which iteratively increases the likelihood at each step and converges toward a stationary point of likelihood surface. Starting from the solution obtained at the highest temperature T, the path of the solution is computed by gradually increasing lambda. For each trial value of lambda, the corresponding solution is computed by a two-step iterative procedure. Namely, expected log likelihood is maximized at the M step, and the expected assignments are computed at E step for unlabeled data. The E step uses Gibbs distribution to compute the expected value of labels as shown here. which distributes the probability mass according to the current estimate posterior NP. For labeled samples, Gm is equal to delta MYI. The M step then consists in maximizing the expected log likelihood with respect to theta, as shown here. Whereas the expectation is taken with respect to the distribution from G1 to Gm, and theta S is the current estimate of the model parameter theta. For more details, please check with these references. Thank you. Bye.